Hi guys, and welcome to Mindset Learn Extra. This is grade 10 science, and tonight's show is brought to you by Liberty. Last week we covered writing chemical formulae with Tracy, and tonight's topic is chemical bonding, and Tracy will be taking us through it.
Hi, Nina.
So guys, please only send us through questions relating to this topic. If there's anything you're stuck with, we'll try and answer as best as we can, and also we'll be going through sections throughout the year that you have difficulty with. So, anyway, next week our topic will be transverse pulses and waves. So lots of you have been asking us about our schedule. So if you're in a group, the topics next week is transverse pulses and waves. The show tomorrow, or the show tonight actually, we'll start off with the lesson on chemical bonding, and then after the break we'll work through an example or two. Then lastly, we'll tackle your questions on the topic. So, there are lots of ways to get hold of us, guys. You can phone us, or you can email us, or go to our Facebook page. That's Facebook, www.facebook.com/learnextra. Our Twitter handle is @learnextra, so get chatting. I'm sitting behind the desk and I'm chatting to you. So while you're watching, shoot us questions and we'll get round to them in the third part of the show. I have a Casio calculator to give away tonight for one of the best posts on Facebook. We will be announcing the winner tomorrow on the Facebook page. So guys, what we're going to do is we're going to go to a Facebook break. We're going to go to a little break and we'll be back with you afterwards. See you now. Hi guys, and welcome back. We are super excited about an awesome lesson today. And without further ado, we're going to go straight to Tracy.
Thanks, Indiana. Well, as Indiana said before the break, we're going to look at chemical bonding. Now, this is a really important section, grade 10, so you've really got to sit up, pay attention, and try and get the concepts. Now, remember that chemical bonding is the instance of what we're talking about in chemistry, because we look at chemical reactions, we look at chemical properties, and where all that goes. Now, up till this point, you've learned about trends on the periodic table, you've learned about how we classify matter from a macroscopic, microscopic point of view. Now we're going to get to the nitty-gritty of what chemistry really, really is about. And today we're going to look at 3 types of bonding: covalent, ionic, and metallic. Now, it's the first time in your science career that you've heard these words, and these are new, so you've got to pay attention. Now, what I've got is a very simplified diagram, because you see this sort of diagram often in textbooks, and what we've got here is we've got the white circles represent the electron clouds, and then we've got our positive nucleus in the middle, which is where our protons would be. And then what happens here, remember, is we have a second one. Now, when we talk about bonding, here, this is a very simple bond. This only represents 2 atoms bonding together. Now, the reason why I've specifically wanted you to see that we have this overlap, okay, over here in the middle, is because that is actually a very important part of the bond, because that overlap results in a sharing of electrons, and those sharing of electrons is the whole point of the bond. Remember, when we looked at orbitals, we said that they had to come in pairs. Now, atoms bond with each other because they want to fill their orbitals, and they will either do that by sharing electrons, giving electrons away, or taking electrons. But they want those orbitals to be filled. When those orbitals are filled, they get to a lower energy state. So the only reason 2 atoms will bond is they want to get to a lower energy state. Now, what I tell my learners is I tell them atoms are like teenagers. Okay, they like to be at the lowest possible energy state. So it's like when you come home from school, the last thing you want to do is work. You want to go sit on the couch and watch TV. Because that's a low energy state, and that makes you happy. Then bonding gives them a low energy state. Okay, so let's go straight to covalent bonding. Now, we've got a couple of representations. Unfortunately, you can't see my orbitals too well here, so let me just draw these in for you. Okay, so what's happened here? Ooh, it's close enough. Okay, now here we got a little bit of a shared one in the middle. This is this diagram here you guys would have seen before, the one with the chlorine. I'm hoping last year when you did molecules and bonding and stuff, a little bit of bonding, you know, chemical formulas, you did dot molecule diagrams. Okay, I'm hoping those are bringing some bells. And you would have seen this often, where it looks almost like and that's for chlorine, that they've squished onto each other, okay? And what has actually happened there, and I'm going to try and show you with my hands, is the orbitals, the outside orbitals, have come together and they have to overlap, okay? So they have to do this with each other, but if they don't overlap, we can't make a bond. And that's what we're showing there, is that they don't come together and sit together like two balloons, okay, or like my hands putting together like this. They actually have to overlap before the bond can be made. All right, that's very, very important. Now, with a covalent bond, it's the first bond we're going to look at. It only happens between a non-metal atom and a non-metal atom. You cannot get it with any other. It's characterized by this. Ooh, that's close. We'll put that there. It's characterized by the sharing of electrons, okay? That electron pair that's shared is very, very, very important. Now, remember, you've also learned about your diatomic gases before, like hydrogen, chlorine, nitrogen, oxygen, fluorine, bromine, iodine, and you all know they're diatomic, they come in pairs. Now, they come in pairs because when they bond together, we get a shared pair of electrons between them. Or with nitrogen, for example, we have 3 shared pairs. Very, very, very important. Now, another way for us to know whether a bond is covalent, where there will be this sharing of electrons, is to look at the electronegativities of the atoms involved. Now, last week we spoke a little bit about electronegativity, and on your periodic table, whenever you get one, the electronegativities are given, so make sure you read the key. When you take the 2 electronegativities of the atoms involved and you minus them from each other, you will get a value. If that value is less than 1.7, okay, it gives me covalent bonding. It's just a general rule. If that difference is 0, it gives us what we call non-polar covalent bonding. So that's a new word for you, okay? We get non-polar covalent bonding. Now, non-polar is actually quite important because what non-polar means for us is that we have complete equal sharing. So both atoms see the electrons for the same amount of time. So both atoms are sort of duped, if I can use that word, into thinking that they have the electrons all the time, okay? If there is an electronegativity difference, then there's not equal sharing, and we get what is known as polar covalent bonding, okay? Water does this. Water is a very important example of this. Water is a polar covalent bond. Oxygen is more electronegative than hydrogen. Oxygen has electronegativity of 3.5. Hydrogen's electronegativity is only 2.1. The difference is 1.4. It is very, very polar, okay? Which means that there's very unequal sharing, and the poor little hydrogen often looks like he's lost his electron, okay? He doesn't manage to hold on to his electron very well at all. Shame. We feel very sorry for him a lot of the time, and a lot of the time his electron just gets taken off by metals and things that are far more excited to have them. But non-polar, polar, non-polar, equal sharing, polar, non-equal sharing. But covalent bonding, whether it's either of these, means that I have a sharing of electrons, which then completes my orbitals. How do we represent it? Lewis structures is an important structure for you to get. Now, what a Lewis structure does is a Lewis structure shows me the valence electrons. Now, we spoke about valency in one of the first weeks, and we spoke about valence electrons. These only show my valence electrons, because remember, as we go down the periods, we keep adding energy levels. Now, we don't need to see the inner energy levels. They don't do anything, okay? They're not required for bonding, because they're complete. Now, if you look at your group 1 elements, and this is why hydrogen's in group 1, there's only 1 valence electron. So there's only 1 electron drawn. This is an unusual format of it because the hydrogen is drawn with your electron on the side. Generally, we'll draw it at the top. Then we get to group 2. It has 2 valence electrons. Note that we put them separate. We don't put them together, but they're on 2 separate parts. So you can think of, and it's a good way to think of it, is when you look at this, is you can go, well, there should be an electron pair, there should be an electron pair, there should be an electron pair, there should be an electron pair. Okay? So we're looking at the fact that it's almost like our F-bar diagrams where we build them up and we have the 4 orbitals. It's the same concept, but we're only putting them around the atom as we go along. Now, as we go along, we keep adding in, and this actually helps us a lot with our bonding, because if you look at nitrogen, for example, nitrogen has 3, and this moved. Anyway, let's just make sure it doesn't look again, because there we go. Now, nitrogen has 3 open spaces. Ooh, let me change color halfway. Anyway, has 3 open spaces. That means it can make 3 bonds. This is what makes nitrogen so special. Carbon and the group 4 elements, the fact that carbon can make 4 bonds is why carbon has a chemistry all to itself known as organic chemistry, which you're going to get to in grade 11, and I like that section. As we go along, we realize that the electrons, the outer orbitals are getting fuller and fuller and fuller, which means we need less and less bonding, and also this helps us with electronegativity. As we move across, good thing to think about in your head is, would it be easier, for example, for magnesium to gain 6 electrons in order to fill its outer shell, or to give 2 away? I'm hoping all of you are screaming at the TV right now and going to give 2 away. Of course it is. We come down to fluorine and chlorine, and we go, well, fluorine's got 7. What's easier, to give 7 electrons away or to take 1? Absolutely to take 1. That's also why fluorine's our most electronegative atom, because it only needs 1 electron, and it has a very small energy level, and it makes it very, very stable. So that's what it likes, okay? What does that mean for us? Well, if we draw our Lewis dot notations, now this is going to come up, and I want to see the bonding. I've got 3 examples, and they all go from single bond to double bond to triple bond. Hydrogen only has 2 electrons, okay, because it has 1 electron in each of its outer shells. We put the shared pair of electrons in the middle. The bond must go between the 2 atoms involved. That's very, very important. When we come to oxygen, oxygen is in group 6. It can make 2 bonds. That means it can make a double bond with itself, okay? Please take very careful note of where I've put the other electrons, okay? Also, I want you to see, now some teachers do this, and there's nothing wrong with it, it's just a way for you to see, but we really shouldn't put this in our diagrams, is there is my oxygen, the 1 oxygen, and we've got 8 electrons around it. Here's my second oxygen, also got 8 electrons around it, and there's our shared pairs. And if I draw a line from each of these, that shows I have a double bond. A double bond simply means I have 2 pairs of electrons being shared. Nitrogen's the same. Now, this is why nitrogen forms a triple bond. It's also why nitrogen is so inert, because this triple bond is extremely strong, okay? Is if I circle that nitrogen, it has 8 electrons. If I circle my other one, it also has 8 electrons. Happy, okay? Plus, I can see that I have 1, 2, 3 shared pairs. So the nitrogen is very happy because it has 3 shared pairs, but it's got C's 8 electrons. Happy as a pig in mud, as the saying goes, okay? But this is all well and good because these are our diatomic elements. What happens when we look at ones that aren't diatomic? Okay, so now I've got some extra examples for you, and these are ones that you're going to see quite often. They're very, very popular. Grade 10s, also in some of your books, you will notice that they use dots and crosses. The crosses are there so that you can differentiate between the 2 atoms and which electrons come from which. But please remember, because sometimes that leads to the misconception that the electrons are different. No, they're not. Whether the electron comes from hydrogen or chlorine, it's still an electron, okay? And in fact, Lewis, when he did the system, only used dots, okay? The crosses are just there as a guide to help you. All right, so if we look at hydrogen and chlorine, hydrogen gives 1 of these little electrons, chlorine gives the other 7, okay? And here is my shared pair, single bond, very happy. Water, now we've got to say, well, how do we know where the hydrogen must go? Because that's a very common question. If we go back a step and we go, well, oxygen has this Lewis structure. Okay, so we've got its 6 little electrons, and the 2 open spaces are right next to each other. These open spaces are exactly where the hydrogen is going to want to bond. It's not going to want to go anywhere else because hydrogen only has 1 atom. So that's how I know that then I would put my hydrogen over here, and I would put my other hydrogen over there, and that gives water its nice angular shape. Okay, and I sometimes teach my kids, it looks a little bit like Mickey Mouse ears. Okay, so if you draw it in a dot molecule, I'm hoping you've seen this. You probably would have been told. We often draw it so it looks like that. Okay, with the oxygen in the middle, 2 hydrogens on the side, and we know it's going to look like that because of its dot molecule, because of this, the Lewis structure. Okay, hope you hanging in there. And then ammonia, very, very, very important molecule as well. Nitrogen has 3 empty spaces, so nitrogen can take 3 hydrogens in each of these, and it goes and it fills all the empty spaces. This pair of electrons here at the top has a very special name. They are called a lone pair. Okay, now a lone pair is just that. It's a pair that stands alone. They're not bonded to anything. Oxygen has 2 lone pairs. Hydrochloric acid has 3 lone pairs. Now those lone pairs are actually quite important when we look at intermolecular forces and stuff a little bit later on, so we're not going to spend too much time on that. Alright, so basically what you need to get from covalent bonding is that it's a sharing of electrons between nonmetals. Getting on to our ionic bonding. Now ionic bonding is so important. Sodium chloride, you see this all the time. It is very, very special. It's the bonding between a metal and a non-metal. Now what happens in ionic bonding is the electronegativity difference between the atoms involved is so big that the chlorine or the non-metal will take the electron away from the metal. I usually, to help my learners remember it, I usually tell them the metals are like really bad parents. Okay, they're not really concerned about the electrons. In fact, they're like, okay, if I've got it, I got it. If I don't, oh well. Okay, but chlorine wants them desperately. Okay, now what we've got is, this picture, the one on the side didn't come out as well as I would have liked, but this shows this middle picture shows such a nice structure of what your ionic bond does. It creates a crystal lattice. And your ionic solids are generally quite hard, they're brittle, they break, they shatter. Your covalent solids are quite malleable. They're not as hard, they're not as, they don't shatter, they're not brittle. It's like candle wax is a very good covalent solid, okay? Now, we've got to add in a couple of extra words that come here because our metal gives away its electron, okay? So it becomes a positive ion. Now that makes it a cation. Okay. Now I remember that the cation is positive because I quite like cats. So it's a cation, so I quite like it, and that's a positive thing. Okay, so that's your metal. Your non-metal gains an electron and becomes an anion. And now anion looks a little, and it's bad spelling, but it looks a little bit like the word onion. And onions make you cry because they're negative. Okay, so your cations are positive, your anions are negative. Your nonmetals always become negative. There are no exceptions to this. And when these bond together, we don't talk about, so when I say that I've got sodium chloride, this is what we call a formula unit. Okay, it's not the same as a compound because only covalent molecules are considered to be compounds because of their bond. This is a formula unit simply because it is practically impossible to separate a single sodium ion and a single chlorine ion in sodium chloride. You cannot get a single one of these. It's virtually impossible. However, with your covalently bonded substances like water, ammonia, it is possible to get a single molecule. But it's difficult, but you can do it. You can't do it with your crystal lattices because now these are held together. They're so strong because we've got positive ions, negative ions, and the electrostatic forces, which you learned about in grade 9, are very, very strong. So they have a positive charge bonded to a negative charge. They're very attracted to each other and it holds very, very tight. Okay, it's also why sodium chloride has, or any of your ionic solids have a high melting point, high boiling point. They're always pretty much solids. You don't get them in gas form. Okay, in terms of how we show this with Lewis structures, now we've got to show the difference in the fact that we're not sharing electrons, we're actually transferring electrons. And we show this by going, well, sodium has a single little electron, which it's going to give to the chlorine, okay? And what happens is we get a sodium ion and we get a chlorine ion, okay? And when we write it in this way, I show the positive and I show the negative. And that helps me get to the fact that the formula is NaCl, okay? If we were looking at, let's use magnesium. I just want to show you one more example, okay? So magnesium, which is in group 2, okay? If we add it to chlorine, and we have chlorine, which is in group 7, and we go, well, my magnesium is going to give its electron away. Can you guys see that there's a problem here? Because magnesium still has another electron, but chlorine's taken it, which means I actually need to have another chlorine here. Okay? And what's going to happen now is my magnesium's going to get very happy because it's going to give its electron away. How do we represent this now? Because we don't want to have to keep drawing everything. So when we draw it here, we go, well, magnesium has become Mg2+, because it lost 2 of its electrons. And what we have is 2 chlorine ion negative ions. We have 2 of them. But do we ever write a chemical formula with the number 2 in the middle? Of course not. That's the little 2 that becomes our subscript, which means we would then write this as MgCl2. Okay? Now, you've learned a whole bunch of rules on how to do formulae, but this is also one way to work it out for yourselves. Okay? Now, our last bonding. Okay? Our last bonding. Metallic bonding is very special. Metals, we call it metallic bonding, but it's a little bit misleading because metals don't really bond with each other, okay? Because they just don't. They form what we call alloys. They form metal mixtures. By metallic bonding, what we're referring to here is what keeps metals as metals. Why do they stay together? And their bonding actually explains why they're good conductors of heat, why they're good electrical conductors, why they're malleable, why they're ductile. It's because of their bonding. Now, most of our metals have got quite a few number of energy levels. So their outer electrons are quite far away from the nucleus. So, you know what? It's a little like that old nursery rhyme about the woman who lived in the shoe and had so many children she didn't know what to do. It's the same thing. These poor little atoms have no clue what to do with themselves because now we've got all these electrons and these little nucleuses are like the parents going, I can't keep track. So what actually happens is we form, the nucleuses stay put. They sort of go, this is my house and I'm staying here. And as long as they can see enough electrons, they don't care where they come from. So what it means is the outer energy level of our metal has pretty much, they all just sort of mush into one. Okay, it's a bad way to describe it, but I'm hoping it actually helps you understand it. And my metal bonding has gone for a little bit of has decided to go running around the TV. But anyway, so we have these electrons here that are very happy to move around. So they go from house to house and jump along, and they're very, very happy. So what that means, okay, let me just do this so that it can actually stay in place. All right, is these electrons here can just move, and they move along, and when we put an electric current through it, that means the electrons are forced to move in a specific direction at a specific time. That gives us our current. Any other time, they're pretty much moving randomly. But you've got to get this. The nucleuses, the nuclei, better word, are stuck in place. It is often described as a positive kernel. Okay? It's a positive kernel. That means it's a positive set, okay? It's a positive kernel, and that's the nucleus. plus the first couple of energy levels, okay? And then we have, and now this is quite an important word. I just want to do something quickly just to distract, to get rid of something quickly. Don't want that, there we go. Okay, now, these electrons, these electrons, very important word, are known as delocalized electrons. Okay, delocalized electrons. They do not have a home. They can go anywhere. When we make an alloy or a mixture of metals, the positive kernels stay, electrons can move through. So it's not the same, it's not sharing and it's not transfer. Okay, it's sort of like a smushing of the electrons together. Okay, so we went through that very quickly, but we've gone through the three main ones. All right, so we're going to take a short break, and when you come back, we're going to do a couple of questions. So we'll see you in a couple of minutes.
Hi guys, and welcome back. I hope you're having a great session. I know you are, in fact. Guys, if there's anything that you are struggling with, please put the questions on our page and we will get Tracy to answer them just now in the third part of our show. Before I go back to Tracy, I just want to say something that I'm very proud of is Sizwe, you know what you're doing. What Sizwe has done on the Facebook page, which is facebook.com/learnextra, that's an X with a XTRA. Sizwe has been posing questions to mindsetters, challenging questions, and I know that Rafense has been answering them as well as a few other mindsetters. Guys, I think that's great. If you guys want to test each other, post those questions on the page. Get them to answer those questions. And also, if there's anything you're struggling with, make sure that you post them so Tracy can answer them. Okay? Without further ado, Tracy, back to you.
Thanks, Indiana. Okay, so now you've had a time to digest a little bit. Let's go down to what the nitty-gritty is. And that is things like, what sort of questions are they going to pose? Okay, because that's quite important. So for example, I could say to you, I give you hydrogen, and the question will be, using Lewis structures, show the bonding between two hydrogen atoms. Now we're going to go, okay, well, we've got to start with Lewis structures. I want to show the bonding. So we're going to start with the fact that hydrogen is in group 1, has 1 electron. And I'm going to add a second hydrogen. And the reason why they would give you a question like this, grade 10s, is because what they're trying to test is whether you understand that hydrogen only needs 2 electrons, that it's not going to go and get a whole bunch of them, all right? And to test whether you understand that this is covalent bonding, because I mustn't show a transfer of electrons like we did with the magnesium chloride or the sodium chloride, because this isn't electron transfer, this is electron sharing, okay? So that means we would now draw it like that. And remember, that means that we can't have brackets around the hydrogens because we're not forming ions, all right? We're forming a molecule. And the molecule doesn't have a charge, so we don't have to put that in there, okay? Let's think of another one that comes up quite often that we struggle with. If we look at sulfur dioxide, okay? Now, sulfur is a very special element as well, okay? And sulfur sits in group 4. I think. Yes. Sits in group 4. So, sulfur and oxygen. Now, sulfur sits in group 6. I'm lying to you. It's the same.
Would you like me to Google it for you quickly?
No, I know.
You know, she knows.
I'm actually just testing them.
Oh, okay.
It's all about testing them.
That's
It's very
exactly,
important.
Yeah.
So, sulfur's in group 6 and looks like that. Okay, no sulfur's. Now I really am showing. I need to actually look it up.
Do you want me to? I can. The powers.
No.
of Google.
We'll find. We have the table. This is
Okay.
when you. No,
Okay.
You know what? Let's ignore that one. Let's do another one. So, This is just a little embarrassing.
It's okay. Okay, guys, you know what?
Yeah, no, we'll move on. We'll do another example. We're going
to do another example.
I'll tell you what.
We're going to forgive Tracy.
Please do. What we'll do is we'll see if any mind setters can help me out. How does it?
Yes.
Our Facebook page, guys, and see if any of you can help me out with what the sulfur is, okay? So we'll leave it up to them and then we'll go back.
That's a good thing to do.
There we go.
I like that, Tracy.
It's all about the test.
I like that.
Okay.
I like that.
So let's go to something I can do.
Yeah.
All right. If we look at, and we're going to look at something simple, let's look at HF. Oh, maybe I should have a thingy for you. Okay, hydrogen fluoride. All right, now, hydrogen fluoride is a strange little creature, okay? Because we have our hydrogen, and we have our fluorine, and fluorine sits in group 7. And now, if you go to your electronegativities, and remember I said you've got to have electronegativity difference of less than 1.7. Fluorine's electronegativity is 4. Hydrogen's electronegativity is 2.1. So they have a difference of 1.9. That is huge. But this is not ionic. The reason why I know it's not ionic, it's 2 nonmetals. So it's a little bit of an exception, which also means that the hydrogen doesn't lose its electrons, doesn't become negatively charged, okay, and the fluorine doesn't actually gain, it shares it. But this molecule is what we consider to be very, very, very polar. Remember I said to you that means positive and unequal sharing. Fluorine pretty much looks like it gets the electrons not pretty much all the time. So that's what happens with the fluorine. Actually, hydrogen fluoride is what we call a corrosive acid. It doesn't have a very high pH like HCl, but you cannot store hydrogen fluoride in glass bottles. It eats through glass. So none of your schools will have it, and it's extremely, extremely dangerous. What about, I now say to you, I want silicon oxide. Okay, so I'm telling you, I want to know what the formula is going to be with silicon and oxygen. I'm not going to tell you whether it's got 2 oxygens, 4 oxygens, what the case may be, but silicon is in group 4, okay, and I know that for sure because it's underneath carbon. So silicon, oh, I've lost my yellow, that's gone on holiday. There's silicon's bond, looks like carbons, okay. Oxygen looks like this. Now, here is where things get interesting because silicon isn't a metal or a non-metal. It doesn't really know what it is. It's one of those metalloid things. So we're going to consider this to be a covalent bond, but now I want you to see something. 1 electron can go here, and 1 electron can go there. Do you realize that we have a problem? That there actually isn't enough electrons for the silicon, which means I need another oxygen. Because now the silicon can make the bonds it needs, so it does this. Oops, sorry. And it's going to go here. And in fact, I'm hoping you all recognize that this looks exactly, when I do it nicely, carbon dioxide. Okay, looks just like carbon dioxide. All right, which is actually quite cool. Did anyone on our Facebook page be able to tell me where sulfur is?
Yes.
Yes.
We do. I don't know if I should tell you now. Maybe I'll just keep it a secret.
Well,
it's in group 6.
I thought so.
It's in group 6.
Brilliant.
Yeah.
So let's go back up. I was right. Sure, I should have just stuck with what I knew.
Yeah,
anyway, it's just that I'm doing sulfur dioxide, which means we changing was a bad choice to make because now you're looking at this and you're going, no, this doesn't make sense. It's sulfur dioxide. But now sulfur has 2 spaces, oxygen has 2 spaces. That really means it should be sulfur monoxide. Actually, it's not. The reason being, sulfur is a nice little special element all on its own as well. And in fact, sulfur has the ability to do all sorts of things when it bonds. In fact, sulfur can make 2 bonds, 3 bonds, 4 bonds. And sulfur is very, very special in that sulfur can have up to 10 electrons in its outer shell. Okay? which isn't really great. In fact, it can have 12. It's one of those things. Now, because they said to you it's sulfur dioxide, I have to have 2 oxygens. Okay, so this is a bit of an exception to the rules that I've just told you. That means when we have the sulfur, we're going to have an oxygen, and we're actually going to have the oxygen here when it does this. This is going to be a double bond, okay, and this is a bit of an exception for you guys, and what actually happens here is this oxygen, because of the group 6 thing, does this, and then we have 1 pair of electrons over there. So they sort of like push themselves around, and the electrons jump from orbitals, and that's actually an exception, and it is angular. Sorry, that was a bit of a hard one. Okay, now, let me ask you, now we're going to go do some theory, okay, because these are all nice, and we're drawing the things, but if I had to ask you, so this would be a typical question, where they say to you that we have an ionic bond, and then in a multiple choice question, and we give you options. So I want you to think through the options, and then we'll work through it. So you guys need to listen. So we have an ionic bond, and the first option is they say that the metal attracts the electrons. And I'm hoping you're screaming at the TV, going, not a chance, of course not. So that's not an option for what we've got, okay? And they're going to try and trick you out by using metal electrons. Be careful. Then they say that the non-metal repels the electrons. Then that sort of sounds a little bit better, but no, because the non-metal takes it, becomes negative. Then it says there's a transfer of electrons, and you go, that's it. That's the definition. So you've got to learn the definition of what an ionic bond is, okay? And then the last option for this one was that there's a sharing of electrons. So that's your covalent bond, so you don't need to worry about that one. Now, this is a good question, because this is also another way of looking at it. And the question says, the bond between iodine atoms in an iodine molecule can be best classified as. You only have 3 options. Now, this question, this was in a multiple choice question originally, but this question could be a good one-word answer. So this might be new for some of you. In all your tests and exams, you should be getting a section with one-word answers and multiple choice. This is a good one-word answer question, because I'm saying to you, I want to know what the iodine bond is between the atoms. Okay, so this is what we call an intramolecular bond, not an intermolecular bond, which you get into. And between iodine atoms, we go, well, iodine, it's I2, it's in group 7, it's a halogen, so it's 2 nonmetals. That means it is covalently bonded. Okay? And I think we're done with my set questions for now. So back to you, Indiana.
You know what we're going to do? We're going to go take an ad break, but the only reason why we're doing that is because we're going to give you guys a chance to get all of your questions in. Guys, this is the part of the show where we start answering your questions on anything that maybe Tracy has gone through, you're not understanding, or anything that you just want to know. So stay stuck to your seats, and we'll see you after the break. Hi guys, and welcome back. As promised, we will be going over the questions section. I'm going to start from the top, Tracy. I know she's excited. You know, it's the teacher's best, because I always get to take them off guard a bit. Guys, if there is anything that you have been wondering throughout the show, I know that there's a whole bunch of you that are probably screaming and shouting, yes, me. Then guys, Facebook us. It's www.facebook.com/learnextra. That's with an X, and also chat to us on Twitter. That's @LearnExtra. And I know there's a few of you on Twitter actually saying it's actually great being able to talk to you straight away. So let's get cracking. Are you ready?
I'm ready for this.
Okay, let's scroll up to the top of the page. Okay, this is a pretty interesting one, guys. It's from Referense, and Referense has to say, he said, it is an angular and there is a dipole moment. I think he was talking about the earlier.
SO2.
Yeah.
Referense, you are 100% correct. SO2 is angular, and it does have a dipole moment, but that's actually grade 11 work. So if your teacher's covered in grade 10, she's just been very thorough, which is great, but it is actually grade 11. So don't stress too much about it. You don't need to know a lot about the shape at this point in time, and you really don't need to know that it has a dipole moment. Okay, not at all. So you don't need to stress.
Okay, but it was a pretty good question.
It's a very good question.
Yeah. Okay, let's have a look here. Let me have a look. Sorry, there's so many of you. I totally had it all. And thank you, Jürgen, for also letting us know that sulfur is in group 6.
Well done.
Thank you. Thank you. Okay, this one is from Tumi. And Tumi wanted to know, is chemical bonding theory or practical?
To me, that is a wonderful question because it's a model. So it's not really theory and it's not really practical, but it's a model. We very much teach your chemistry based on Bohr's model of the atom. Okay, because remember we did a little bit of a history, and the whole model that Bohr has is that we have these energy levels and orbitals. Okay, and at the moment there is a debate within the scientific community as to whether ionic bonding actually exists in the way we teach it to you, that there's this complete transfer of electrons. So to simplify things for school level, we need to stick to a model. So it is a way for us to explain what we can see in practice. So remember, we have macroscopic and microscopic properties, and we can see that things that we say in our model are covalently bonded, behave in a certain way, have certain macroscopic physical properties, where things that are ionic, like table salt, behave in a certain way as well. So our theory of covalent ionic metallic bonding is just a model. It's a way for us to explain microscopically what we see on a macroscopic level. It's actually something that's really difficult to get to the point where we can go, well, this is 100% what it is, because in fact the scientists at CERN in Switzerland have, they're forever trying to find extra little particles, and now the debate is actually whether electrons exist at all as particles or whether they're just waves. So we don't really want to confuse you with things like that, so we stick to a model, okay? And I'm hoping that helps you. Yeah.
Well, guys, we've actually got fab questions coming through, so thanks. Okay, ready? Yes. Okay, Taborka wants to know, which I find quite interesting, can we use crosses instead of dots in the Lewis structure?
Absolutely, Taborka. There's nothing wrong with that. If that's what your teachers taught you, go ahead. So for example, if we go back to the hydrogen one, okay, so now I did it with dots, so you probably been taught to do it with crosses, and they were probably done at the top, and that's fine, because what your teacher's trying to show you is dots and crosses, just so you can see that your electrons come from two different atoms. There's nothing wrong with that, though technically speaking, it should all be dots, but it should be marked right. There's nothing wrong with it. Yeah.
Okay, here's another one. Tracer. Okay, Anugrah wants to know, says, according to the group number, we can know, I think he means to say, how do we know the valency of each element easily, but what about transitional metals?
Transition metals are taken to be 2, except for silver. Silver's taken as 1, unless they give it to you in your name. So when they're looking at something like tin, if it's tin 2 oxide, and they will write it like this for you, they'll say tin 2 oxide, then that means tin has a valency of 2, but if I take tin 4 oxide, then it has a valency of 4, and they have to tell you that. So your transition metals generally have a valency of 2, unless they tell you otherwise, and silver is the exception that has a valency of 1. Good question. It's important for you guys to know that.
Yeah, guys, loving the questions. Keep them coming through. We do still have a few more minutes. Tapelo. Okay, Tapelo says, how does sulfur make more than 3 bonds and can have more than 8 electrons in the outer shell?
Because sulfur sits, now I should have actually put this up earlier when I wasn't really sure where sulfur was. Sulfur sits in the 3rd period. Now it's very close to the 4th period, where we start getting our D and F orbitals, which are orbitals we don't deal with in grade 10. In fact, we don't deal with them at school level, which actually means given enough energy, this sulfur atom can expand its energy levels for the D and F orbitals. So it's just a very special element, okay, that has the ability to actually contain more electrons in its outer shell than the normal, okay. So it's one of the exceptions, because things like boron, which is another exception, likes to only have 6. So instead of obeying our octet rule, which says we have to have 8 electrons, boron likes to have 6. Warren's very happy having 6. So you're not going to have to spend too much time on that in grade 10. You will follow it up in grade 11. In fact, my grade 11s hate me right now because we're busy dealing with this, and they think they hate all the exceptions, but you're only going to have to do a couple, and sulfur's one of them, and phosphorus as well. Phosphorus also has the ability to have more than 8, but there's very specific examples when that happens, so you don't need to stress about that too much this year.
Cool.
Yep.
Guys, the questions are coming thick and fast, and I'm loving it. Santiago wants to know, can electrons in the form of dots be placed anywhere around the symbol?
No, they've got to go in pairs. So when we look at, even when you're setting it out, so phosphorus, now it looks like it's just anywhere, but it's not. Because our phosphorus, we would fill it up like we fill up our orbitals. So at the top, at the side, at the side, and at the side. Now each has got one, and then we start again at the top. So no, they have to go in pairs, and they have to go top side, bottom side. So they can't go wherever you like. Yeah.
It's incredible.
Probably have time for one more, I think.
Okay, one more. Where's a good one? Okay. Guys, I'm sorry. There's so many good ones coming through. Let's try Sianda. Okay, Sianda. Why is an ionic bond one or more electrons are transferred from the metal to the non-metal?
Because, and actually I've got the right thing on the board at the moment, is because of when we look at our structure, and this is actually moved shame. Anyway, when we look at the structure, your metals have very few electrons in their outer shell. And remember, the whole point of bonding is to get to our noble gases, full energy levels. So you got to remember, it is much easier and takes far less energy to give away those 2 electrons than to take 6, which is what it would need to do in order to get that full energy level. Okay? So your metals, and also remember how the metals bond within themselves, is that they have that positive kernel with those delocalized electrons. It's easy to get those electrons to move. The non-metals are very, very close to the electrons. Because and remember, they're smaller atoms because they're of the extra positives and negatives. So they're much smaller. The forces of attraction between the protons and the electrons are much stronger. So the non-metals will take when the metals will always give away. It's just because of their structure. Okay.
Okay, cool. I think we've got another quick one. I think we might. It's a quick one. It might even be able to 2. Are from Karabo, and Karabo wants to know, are isotopes made or are they already there?
They're already there. Isotopes are actually quite important. Remember, the only difference between elements when they're an isotope is they have different mass number, which means they have a different number of neutrons. It does not affect their bonding. It doesn't affect what we do with them, and they're natural. We cannot make isotopes, okay? As far as I know, we can't, because we can't change the number of neutrons, but they're just natural. They're there. The way it is.
It's awesome. Okay. I hope I'm not going to make an edit out of myself. Lloyd says, can you use the off-by diagram to know where electrons are?
Yes, we covered that last week.
Okay.
Because we looked at the SP note, we looked at the notation as it went up, so absolutely. But the off-by diagram gives you a bigger structure, whereas the Lewis gives you the valence structure, which is actually more important in the long run. Yeah.
I see. Okay. Now I just need to find one more question. Let's see.
Yes, I think 30-second question.
30-second question. No stress, no pressure at all. Let me see. What does it mean when they say, oh, have I asked this one? Okay, tell me if I have. What does it mean when they say metallic bonds have a low first ionization energy?
Okay,
that's from
that one. No, that's actually a really good question. We wouldn't say metallic bonds have a low, but metals have a low first ionization energy. Now, first ionization energy, remember, is the energy required to take an electron off a atom in the gaseous state. So what's easier, to take lithium's little electron away, or to try and take one of fluorine's? So not fluorine. So metals have a very low first ionization energy because it's easy to remove the electrons. Your non-metals, very high first ionization energy level. Okay, that was a really good question.
Yeah. Well done, Rafense. You've been amazing. Rafense has been amazing on the page today. There's been a whole bunch of amazing mindsets on the page, guys. Thank you so much for answering questions, asking questions, helping each other out. That's exactly what we like to see. Today has been a fantastic session. Thank you so much, grade 10s, grade 11s. Stay stuck to your seats because you're on next. Grade 10s, goodbye.